We have completed till now the semiconductor in equilibrium. Okay, we have discussed about the concentration in intrinsic semiconductor. Also, we discussed about the how to calculate the concentration in extrinsic semiconductor extensively. Okay. Also, we have covered how the carriers are transported in a semiconductor. Mainly, we have seen what is a diffusion transport, what is a drift transport, right?
Okay.
Okay, so today we will see, we will start diode, but before that, there is an important topic that is like if I give you a new device, right? So then what are the things that you need to know about the device? Okay, like basically what is the electric field inside the device, what is the concentration of carriers inside the device, how the transport will occur in a new device if I give you, suppose if I give you some device structure, okay, so then you should how to analyze based on which equations, okay. So whatever till now we covered, using this we will form an equation called continuity equation, okay. So it will have it will give you a way to analyze a new device, fine. So we'll start with that continuity equation. Equation. Fine. So, am I audible clearly?
Clear, sir.
Okay. So, what I'm asking, suppose there is semiconductor, okay? Suppose there is semiconductor, right? So, to which suppose I illuminate with light, okay? Light I'm illuminating, okay? So, the energy of the light or photon I can say is greater than the band gap, right? Energy is greater
Right.
than the energy gap, okay? So, what will happen? It will try to break the bond, okay? And electrons and holes will be generated, right or not?
Right, sir.
Right. So let us assume that I am putting light all over the semiconductor. Okay, and they are generating uniformly over the entire semiconductor. Okay. So what I am asking, what is the net what is the net generation rate? Okay. So if I want to calculate, what is the number? Suppose I want to calculate the number of holes increasing per unit time. Okay. So suppose I want to calculate dp by dt. What is the meaning? I want to calculate the rate of increase of hole concentration per unit time, right? This is what I want to calculate, because hole and electrons are generated. Okay, what I want to calculate the rate of change of hole concentration, right? This is equal to generation rate minus recombination rate, right? So generation rate minus recombination rate will give me the net increase of hole concentration per unit time, right or not?
Right.
Right. And since I am assuming that the carriers are generated all over the volume uniformly, okay. So definitely, since there will not be any concentration gradient or anything, so there will not be any movement of carriers inside the semiconductor, right or not? There will not be no net movement of carrier, because they are generated uniformly throughout the semiconductor. So there won't be any net movement of carrier inside the volume, right?
Right.
Right. So this recombination rate is given by the change in concentration by the lifetime of carrier. Okay, this is formula. Like this is the whenever the carrier is generated, they will stay almost lifetime. So this recombination rate is the generation rate divided by the tau, lifetime of the carrier. Okay, so this is my continuity equation if the generation is very uniform throughout the volume. Okay. So if I want to write it in this rate of increase of hole concentration.
So my slide was actually updated right now. So from
Ah,
where that tau we have written, sir?
no, no. The recombination rate is okay. The excess carrier divided by the lifetime.
Okay, okay, okay.
This is the recombination rate. Okay, so G is the generation rate, number of carriers generated per unit time. Okay, minus the number of carriers recombining per unit time will give me number of rate of increase of hole concentration.
Okay,
Okay,
okay, okay.
this two is called net generation rate. Okay, this is my continuity equation. If the generation is uniform throughout the volume, okay, and so that there won't be any net movement of carrier from one place to another place. Okay.
Okay.
Suppose there is the generation is not uniform. Okay, somewhere like the carriers are generating more, somewhere less. Okay, so in that case, can you see my cursor?
Yeah, clear,
Yeah.
clear.
Yeah. So can you able to see my this cursor?
Yes, sir. Yes, sir.
Yeah. So what I'm telling, suppose the generation is not uniform. Okay. So there will be non-uniform generation. What will happen? Suppose in this region, the generation is more. In this region, the generation is less. Here more, here is less. So definitely they will try to diffuse from higher to lower. I don't know. Here the carriers are generated more. Here it is less. So definitely they will try to move from higher generation rate to lower concentration. I don't know.
Right.
So in that condition, how to write the continuity equation? Suppose the generation not uniform. Okay, how to write? That is the called, that is more general concept. Suppose you take a, okay. So in that case, how to write the? Okay, this is my semiconductor. Okay, so here the carriers are generating non-uniformly. Okay,
Okay, okay.
so what is the meaning? There may be a motion of movement of carrier from one place to another place. Like in here, it is uniform. They are not moving here and there. But here, there may be a movement of carrier from one place to another place. Right? Suppose we will take a little volume in this volume. Okay. So in this volume, suppose I want to know the rate of increase of hole concentration in this volume. I want. Fine. This is my aim. Okay. So this is my semiconductor. Okay. It is there. Yeah. Okay, so but so that the area is suppose unity. Okay, the area is unity. This is the area. Okay, this area equal to unity. So I am considering only one dimensional case. Okay, so what is my question is, in this volume, right? Okay, suppose this volume is length is dx. Okay, and area is there. Area is there. Okay, this area is there, which I am neglecting. This area is unit area. Okay, getting in this volume, I want to know the net net increase of hole concentration per unit time. Okay, so what will happen? Because of non-uniform generation, right? There may be some current entering into the volume. Okay, suppose that will be Jp into x. Okay, because it is non-uniform, there may be some current entering into the volume. I don't know, some neighboring area. Okay.
Right.
Also, there may be some current leaving from the volume. Okay, that will be Jp x plus dx. Dx. Right. So this is the because of non-uniform generation, some current may be entering to the volume, some current may be coming out of the volume. Okay. So definitely in this volume, there may be some number of hole input because of non-uniform generation from the neighboring sites. Okay. Also, there is light. There is light like earlier cases. Okay. Along with since the generation is non-uniform, there may be some current entering into the volume, some current entering out of the volume. Okay, so in that case, how to calculate the rate of increase of hole concentration? Okay, so rate of increase of hole concentration, okay, will be equal to, okay, like earlier in this volume, whatever may be generation rate, generation minus recombination rate, right?
Right.
Okay, that is called net generation rate, okay, plus net rate of hole input the volume. See, because there is some current input entering, some current is leaving, okay, so definitely there will be some number of carriers entering from neighboring side, right?
Right.
Yeah. So it will be net rate of hole input, right, into the volume. Volume. Okay. So if I write mathematically, what will happen? So the net increase of hole concentration is nothing but d by dt of what is the volume? Volume is the concentration, okay, into dx is the length into area is unity. Okay. This is the rate of increase of hole in this volume, right?
Right.
Within this volume, I am talking about in this volume. Okay. This is the volume is equal to generation minus del p by tau like earlier, okay, plus there is some current is entering. Current means nothing but rate of flow of charge, right? Flow of charge. Then if I want to know the number of carrier, what I have to do? So this should be 1 by charge into, okay, jp of x minus jp of x plus dx, okay, into this is the number of charges and number of carriers entering into the volume per unit area into area is unity, right? J is nothing but current per unit area. So if I divide current by charge, I'll get number of carrier per unit area entering, right? This is the number of carriers entering per unit area into the volume. This is JPX, right? JP is what is current? Current is nothing but dq by dt, right? Number of charge carrier entering. If I divide by charge, I'll get number, right or not?
Right.
Right. So the JPX is the JPX by Q into area is unity. Okay. So this is the number of carriers entering into the volume. Okay. Minus number of carriers leaving the volume is JPX plus DX is the current leaving this volume into area by Q. Is this equation clear to you?
Clear.
Yeah. So this is the net rate of increase of hole concentration hole in the volume dx. Then this is the net generation rate inside this volume. Then this is the net input of holes because this current is entering, current is leaving. Current divided by Q is the number of carriers into area is the number of charges entering. Right?
Right.
Okay. So then if I do this one, what I will get? Then this will be equal to, if I divide dx by both sides, okay, this will be, this is for unit volume. Here also you have to multiply dx into 1 because you are calculating the entire volume. This is the generation rate per unit volume. Okay, you have to multiply dx into 1 is the volume. Okay, for to getting the net generation inside the volume. Clear?
Clear.
Like in this you see, this is the per volume. This is also per volume. Now I want to know in this volume, means I have to multiply the volume. Here I multiply the volume. Here also I have to multiply the volume. Okay.
Okay.
So if I dp by dt is equal to ds, if you divide, you get g minus del p by tau, okay, plus 1 by q jpx minus jp x plus dx by dx. Okay, if dx will be very small, okay, how to do? Then it will be the derivative of current, na? Okay.
Yes. Limiting.
Yeah, limiting factor. So dp by dt is equal to d dash minus del p by tau minus 1 by q into 1 by q into djp by dx. Because djp by dx means what? This is Jp into Jpx plus dx minus Jpx by dx. When dx is almost comes very, very small, then I will convert into like a derivative, right? But here it is
Right.
Jpx minus Jpx plus d, so that's why there should be minus here. Clear?
Right.
So this is the continuity equation for hole. So let me write it clearly. It will be dp by del T is equal to net generation rate minus 1 by q into djp by dx. Okay, this is my continuity equation for hole. Okay, what it tell? The net increase of hole concentration, right, equal to net generation rate plus, actually this is actually plus, okay, plus the net rate of hole input. Clear?
Clear. Clear.
So see why this this is minus. Okay, suppose I want to know for electron, it will be dp by dt, right? dt is equal to for electron equal to, okay, I have generation minus recombination is the net generation rate plus 1 by q d jn by dx. Getting?
Getting.
Yeah. Why? Because this is plus. Because you see, I am calculating the number of carrier entering. Okay. If carrier entering is like this, then the current will be opposite of the electron flow, right? Here, whole flow and the current flow is same direction, right? But if I consider electron, if I tell what is the number of electron entering, then the current will be leaving this space, right?
Right.
So that's why this minus is there. Minus will become plus. Okay.
Clear.
Okay. So this is the continuity equation for electron. What did it give? It gives the net rate of increase in hole concentration is net generation rate minus plus the net input of hole. Okay.
Okay. Okay.
Okay. So one more thing is important is called Gauss law. Gauss law you might have studied in EMT, right? So EMT somebody is teaching you, right, in this?
Right now, no one started.
Oh, right now it's not started.
It haven't started yet.
Okay. Okay. So let me tell you what is this Gauss law. Okay. Suppose what it tell na, the number of electric field line that is coming out of a volume, okay, is nothing but, I can say, the number of electric flux lines, not field lines. Okay, number of electric flux lines coming out of a volume is equal to the total charge content into the volume. This is the Gauss law. Okay, suppose I'll give a simplified expression of Gauss law. Okay, suppose this is the electric field line entering. Okay, this is the electric field line leaving. Okay, getting?
Okay.
So the electric field line leaving is more than electric field line leaving if there will be some positive charge in the volume. Getting? Means the electric field, because of the positive charge increases, positive charge in the volume, there will be some increase in electric field. It will be E plus DE. So the DE will depend upon the how many charges there inside the volume.
Right.
Because charge is the source of electric field. So there is some electric field entered. Then by leaving, right, we have some more number of charges in the volume. So the leaving electric field will be E plus DE. This DE will depend upon the number of charges inside the volume. Okay.
Right.
Okay. So the increase in the field, okay, is nothing but, if you see increasing flux, actually, okay, flux means it will be, suppose the area is unit, okay, the area is unity, okay, area equal to unity. This is dx area equal to unity. Okay. So what is the d? Del d. The d is nothing but a flux. Okay. We'll see del d is the number of flux increases in this volume. So the total flux increase in the volume is d into area into the distance dx. Okay, and calculating the distance dx. Okay.
Okay.
This is actually if you see the distance dx. Okay, this is the area. Okay, the area actually unity. Fine. Fine, na?
Fine, fine.
Okay. So what I'm telling in this living, right? The increasing flux, nothing but del D is the increasing flux. The flux per unit volume into the volume is the number of flux increases. Clear?
Okay, okay.
Equal to the total charge contained in the volume. So suppose the volume charge density is rho v, is the volume charge density per unit volume into dx is the length into area. Okay. So this is d is the flux. Okay. So the total flux increases per volume into the volume is the total flux is equal to the total charge contained in the volume. Let the rho v is the charge per unit volume and multiply by volume, right?
Right.
And we know d is nothing but epsilon into electric field. You know, na?
Right.
Equal to rho v into dx. Okay. Del d, okay. Del d will give you flux per unit area. Okay, have to multiply area to get the total increase in flux. Okay. Del D is the total flux per unit area. Okay, here multiplied by area, I'll get the total increase in flux. Getting?
Okay.
Okay. So then I will get epsilon into D is equal to rho v into dx. Okay. So that I will get rate of the electric field, the change of electric field will be equal to rho v by epsilon. This is my Gauss law. Okay. So Gauss law, what it tell? The living electric field is more than the entering electric field if there are some charges inside the volume, right?
Okay.
And the total flux increase is equal to flux per unit area into area equal to the total charge in the volume. Charge is equal to, this is the volume charge density, charge per unit volume into dx into 1 is the volume.
Right.
Right. So this will give me my total change of electric field per unit distance.
Okay. Okay.
Okay. So there is nothing but I can say this will give you the gradient of flux.
Okay. Okay.
Okay. So now we call Gauss law. Okay. So now there are two things I'm just summarizing now before leaving. So what are the equations we have seen? Let me take a table. This you understood that this is one content equation, right? So content
Right.
equation is nothing but this one. Rate of change of hole concentration is net generation rate minus plus the net rate of hole input. Similarly for the electrode. Okay. Then another is Gauss law. Gauss law is nothing telling that the net increase of flux lines in a volume depend upon the how much charge content in the volume. Right?
Right.
Okay. Now I will just summarize what are the equations we have for analyzing. Okay. So I will explain you what are the equations that you have for analyzing the semiconductor device. Okay. So see here. Okay. So here is the, sorry. Okay. So I'm summarizing what are the equations we are having. Suppose you give if you get a new device, right? What are the equations you have in your hand to solve all the quantities that is needed? Okay. So
Okay,
first
okay.
thing is Jason. Okay. So carrier. Okay. One is because of electron, another is holes. Right. So what are the equations you have? We have seen the transport equation. Right. Right. What are the transport equation you have seen? The current due to the electrons equal to drift current plus diffusion current. Hello.
Hello. Yes, sir.
Yeah. So we have seen this. The transport equation is nothing but Q M V1 into electric field plus Q dN by dx. This is the drift
Yes,
current
yes.
plus diffusion current, right? This you have seen. Okay.
Right.
Well, for holes, what is that? Equal to Q hole concentration into mobility of holes into electric field minus Q into d dp by dx. Okay. Why this minus is there? That is your understanding. Why here it is plus? Why it is here it is minus? Are you understand? Are you getting this? Why this is there? Because if you understand the physics behind this and you will remember, you will forget, you will definitely going to do a mistake. Why this plus minus is there?
um,
Yeah. Can you tell me? Hello.
yes, sir. Audible, sir. Just taking.
See, I will tell you why the diffusion equation have a minus here. Okay. Suppose there is region 1 and region 2. Okay. And the
Okay.
whole is more here, whole is less here. Okay. So the profile is like this. Right?
Right, right.
So this is the concentration with the distance. Clear? So the whole will move from 1 to 2 or 2 to 1?
1 to 2.
1 to 2. Okay, they will move like this. Right? And
Right.
what is the whole current direction? Like this only.
Yes, 1 to 2.
So the whole current direction is same as the whole moving direction.
Yes, yes.
Okay. So it should be positive in this case. So this is, if I say this is positive x, so it should be positive, no?
Yes, yes.
So, but if you see the gradient here, whole is nothing but q dp by dx. Okay. So if you
But
see
it's
here, the gradient is negative or positive?
gradient is actually negative.
Yeah, negative, right? So see,
Yes,
see
yes.
if I put just like this, right? Then if you calculate this, you will get negative current, na?
Yes, we should. Okay.
Because here the gradient is negative.
Okay, okay, okay.
Okay. So you have to put a minus here because the whole current is exactly opposite of the gradient. Here see, here gradient is positive, gradient is negative, but whole is flowing in, current is flowing in the positive x direction.
Clear, clear.
If I don't put this minus, it will be negative, so I'll get negative current. So what it will mean, the current will be flowing in the negative x direction. If you evaluate without a minus, if you evaluate, you will feel that current is flowing in the negative x direction. I don't know.
Right, right.
right? So that's why this minus is there here. Suppose this would have been electron, okay, other than, so this would have been electron, okay. Okay, now analyze 1 2, this is electron, okay. So electron will flow from like to like this, right? So when electron will flow like this is electron flow. What is the current flow direction? Left or right?
Convention.
Opposite, na?
Opposite.
Opposite. So in this case, if you do q dn, dn by dx, so dn by dx is negative here, so the current will become negative. So it's okay for us, because current should become negative only.
Okay.
So now understand the physics behind this plus or minus?
Clear.
Okay. That's why you should not remember anything in these equations. Otherwise, you are gone.
Right, sir. Right.
Okay. So another thing you are seeing is continuity equation. What is the continuity equation for electron? It will be change of hole concentration LT equal to, right, 1 by q d jn by dx plus generation minus recombination, right?
Right.
Similarly, for whole it will be minus 1 by q d jp by dx plus g. Okay, so here also the minus will be coming from some similar region only. Okay,
Right. Sir.
okay, then there is something called flux. Okay, so in continuation, what is the flux distribution? We have no d by dx, change of electric field with respect to distance is equal to, okay, nothing but volume charge density by epsilon, right?
Right.
Right. Also, you know, electric field in transport equation is equal to minus the gradient of potential, the potential, okay. I can say dv by dx, right?
Yes, sir.
Okay. So these are the basic equations that we have understood till now. So why I summarized it, using these equations only, whichever device you will get in your hand, right? Using these basic equations, you will try to solve the, suppose you want concentration, right? For concentration, electric field, okay. What are the unknowns here? Current, Jn, Jp, right? Electric field, right? Mobility, sorry, Jn, Jp, electric field, hole concentration, and electron concentration. Okay, these are the unknowns. You need to find out solving all these 5 equations. If you get any devices, getting?
Okay.
Okay, so in these equations, you have to find out the current due to holes electrons, the concentration due to electrons and holes, and the electric field. Okay, so based on these equations, you can easily solve these things for a new device. Okay, so since actually I do not have time, right? Or otherwise I could have taken one example to show you how to use this equation and use in the device. But for the time sake, I am not going to that detail. That is not needed at this point. Okay, so if you get any device, how to use these equations and solve all these quantities. That is the objective of this continuity equation. But since you do not have time, right?
Okay.
That part is not important for the exam. So that's why I am skipping this part. Okay.
Okay.
Okay. So now, before leaving this topic, I want to mention one more thing. Okay. The transport equation you have seen, right? Jn equal to, suppose Jn, okay. I'm talking Jn is equal to what is the transport equation? U n mu n into electric field plus U dn by dx. Okay. So how this can be represented in terms of very compact equation? That I will see. Okay, because in order to appreciate like when the current should be 0, how it will flow. Okay, so how to represent it compactly. Before leaving this topic, we will see the series, then we will go to diode. Okay. So we know here n is equal to, concentration NC into exponential of EC minus EFN by AT. Okay, EFN is nothing but quasi-Fermi level for the electrons, right? This equation is clear?
Clear, sir.
Is there any doubt in this equation?
No.
Okay. So then what is dN by dx? Equal to NC into exponential of, this will be same as this one, minus EC by AT, right? Into derivative of the inside thing, I don't know. So if I do derivative of the inside thing, what I'll get? I'll get
EFN by
dx minus by dx. Clear?
Clear.
So if I derive it, I will get 1 by kt.
Yes, minus 1 by
Clear? If I derivative
Clear.
inside, I will get 1 by kt outside. Okay.
Okay.
Then for this dn by dx, I have to multiply q into dn. Okay. Let's multiply q into dn here. U into dn. Let's multiply u into dn. Right?
Right.
Equal to. So kt by q is what? Vt. Right? Kt by q is Vt.
Yes, BT.
Kt by q is Vt. And dn by Vt is what? Mobility. You know, d by mu is Vt. You know Einstein's equation. So
Yes.
d by Vt is mu. So this can be expressed as mobility. d by Vt. d by Vt is mobility. Fine.
Right.
And what is the NC exponential of this one? Nothing but same as your n only.
And okay.
N only. Okay. Into dx minus dx. Fine. So this is my q dn by dx by dx. Okay. So this now we know qn mu n into electric field is a drift current. Okay. This is my diffusion current, right? This total is my diffusion current, right?
Right. Hello, sir. Hello. Am I audible, sir?